In this lesson, we will learn to integrate functions using a technique called partial fractions. You may have learned about partial fractions in a pre-calculus class, but depending on the content of that course, maybe you did not see this. So this technique lets us evaluate integrals of the form something over a factorable polynomial. So what we're first going to do is take the polynomial inside the integrand and factor the denominator. In this case, that denominator factors into x minus 3 times x minus 1. So we have 1 over x minus 3 times x minus 1. And now this came from combining the denominators on some fraction, a number a over x minus 3 plus some other number b over x minus 1. If you add these two together by getting a common denominator, you're going to get the left-hand side. Now what we do is multiply both sides of this equation by the denominator of the left-hand side, by x minus 3 times x minus 1. And when you do that, on the left we just get 1. When you multiply a over x minus 3 by x minus 3 times x minus 1, you just get the x minus 1. So that's a times x minus 1. Multiply the b by that expression, you're just going to have plus b times x minus 3. Now we distribute. 1 equals ax minus a plus bx minus 3, or 1 is equal to x times the quantity a plus b minus a minus 3b. And now for this to be true, negative a minus 3b is going to have to equal 1. That's the constant. So negative a minus 3b is equal to 1. And a plus b is the coefficient of x, and there are no x's on the left-hand side, so a plus b has to equal 0. And now you can solve this system of equations using either a technique called elimination, where you add the two equations together, or substitution. So if a plus b is equal to 0, then a is equal to negative b, so that when we sub that in, we have negative b minus 3b equals 1. So double negative b makes positive b, minus 3b is negative 2b equals 1. So we get that b is equal to negative 1/2. And because a equals negative b, a is equal to positive 1/2. Now we can input the a value of 1/2 over the x minus 3 and the b value of negative 1/2 over x minus 1. And here's what happens, and we're going to find our integral now. So the integral of 1 over x squared minus 4x plus 3 dx is equal to the integral of 1/2 over x minus 3 plus negative 1/2 over x minus 1. And you can integrate each of those pieces individually. We'll have 1/2 the integral of 1 over x minus 3 dx minus 1/2 the integral 1 over x minus 1 dx. And if you want to do a substitution, you can substitute for the denominators, but since du is just dx, it's easier just to notice that this is 1/2 ln absolute value x minus 3 minus 1/2 ln absolute value x minus 1. Don't forget those absolute value bars, because if you do, your answer is not going to be correct. So in general, when using partial fractions, there are 4 cases, and the first case is that the denominator is a product of distinct linear factors. So first of all, what linear means. Linear factors means you have stuff of the form ax plus b So something in like y equals mx plus b form, so some kind of line, it would be a line if you were to graph it. And distinct means that nothing is repeated. So for example, your denominator cannot be x plus 2 squared because you have the factor x plus 2 twice, not distinct. Not linear would be something like your denominator cannot be 1 over x squared plus 4. That would be a quadratic factor because of the x squared. So distinct linear factors. So evaluate the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. So first step is to break it all up. So we are going to first factor the denominator. So take out a GCF of x, and we'll have x times 2x squared plus 3x minus 2, which then factors into 2x minus 1 times x plus 2. So what we have now is x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2 had to come from some a over x plus b over 2x minus 1 plus c over x plus 2. Now when we multiply by the denominator, we get x squared plus 2x plus 1, plus 2x minus 1, sorry, equals a times, now multiplying a over x by this denominator, the x cancels, but we're left with a 2x minus 1 factor and an x plus 2 factor. So 2x minus 1, x plus 2, plus b, we're left with an x factor and an x plus 2, and then plus c times x and 2x minus 1. Now we distribute. We'll have a times the quantity 2x squared plus 3x minus 2 plus b times x squared plus 2x plus c times 2x squared minus x. And now I'm going to take, at this step, just gather all the common factors. So the x squareds, so we will have x squared times the quantity 2a plus b plus 2c, and then gather all the x's. So we'll have plus x times 3a plus 2b minus c, and then the constant part will be just minus 2a. And this gives us the system. So first of all, negative 2a is our constant term. That has to equal negative 1. So negative 2a is equal to negative 1, therefore a must be 1/2. Alright, next we have the coefficient of x. 3a minus plus 2b minus c has to equal 2. 3a plus 2b minus c has to equal 2. And the coefficient of x squared, 2a plus b plus 2c has to equal 1. Now if I plug in what a is into both equations, this first one, a times 3 will be 1.5. If I take that 1.5 away, I'll have 2b minus c is equal to 0.5. When I plug this 1/2 in for a in the second equation, 2 times 1/2 is 1. I take that away. 1 minus 1 is 0. And I get b plus 2c equals 0. So, the second equation, we could say, well, b is equal to negative 2c. And you can take this and input it for this b. And that gives you negative 4c minus c equals 1/2. Negative 5c is equal to 1/2. So therefore c is negative 1/10. And once you know c, you can go back and find b. Since b is equal to negative 2c, b is equal to positive 1/5. And as you can see, most of the work is in finding these not coefficients, but finding these constants. The integration is not that much work. So now that we found a is 1/2, b is 1/5, and c is negative 1/10, our original integral is equal to an integral of 1/2 over x plus 1/5 over 2x minus 1 minus 1/10 over x plus 2. So that's 1/2 integral 1 over x dx plus 1/5 the integral 1 over 2x minus 1 dx minus 1/10 the integral 1 over x plus 2 dx. Alright, the antiderivative of 1 over x is just ln absolute value x, so 1/2 ln absolute value of x plus 1/5 ln absolute value 2x minus 1. And just think, if you differentiate this, you'll have 1 over 2x minus 1 times 2. So to compensate for that times 2, we need a coefficient of 1/2. And then minus 1/10 ln absolute value x plus 2 plus c. So we have 1/2 ln absolute value of x plus 1/10 ln absolute value 2x minus 1 minus 1/10 ln absolute value x plus 2 plus c. And as I said just a few minutes ago, the hardest part, or the most tedious part of this integration technique, is figuring out what these numbers are in the first place. That's a lot of algebra, and it's really easy to mess it up. The integration part, you're going to often have natural logs and occasionally some arctans and things. But the integration part is not nearly as tricky as the tedium of finding those constants. So find the integral of dx over x squared minus a squared. So a is a constant, not a variable. The dx tells you that x is the variable. And actually, x squared minus a squared factors into x plus a times x minus a. So we have 1 over x plus a times x minus a is equal to capital A over x plus a plus capital B over x minus a. And now if I multiply by x plus a times x minus a, I have 1 equals capital A times x minus lowercase a plus b times x plus lowercase a. And gathering coefficients, I have 1 equals x times capital A plus capital B. And then I have minus lowercase a capital A plus lowercase a capital B. Okay, because there is no x on the left-hand side, a plus b will have to equal 0. And negative lowercase a capital A plus lowercase a capital B has to equal 1. So this tells us that a is equal to negative b. So if we input that, we will have positive lowercase a capital B plus a capital B is equal to 1. So that's 2 lowercase a capital B equals 1. So b is equal to 1 divided by 2a. And since a equals negative b, a is equal to negative 1 over 2a. Don't be freaked out, a is just a constant. So this becomes, so our original integral is equal to an integral of negative 1 over 2a all divided by x plus a plus 1 over 2a all over x minus a. So breaking it into two integrals and factoring out constants, we'll have negative 1 over 2a times the integral 1 over x plus a dx plus 1 over 2a times the integral 1 over x minus a dx. So when we antidifferentiate, we'll have negative 1 over 2a ln absolute value x plus a plus 1 over 2a ln absolute value x minus a plus c. Now, just so you're aware that you can simplify this, I can factor out that 1 over 2a and write this as ln absolute value x minus a minus ln absolute value x plus a plus c. And properties of logs say that this expression can be condensed into a single logarithm, and that's ln of x minus a divided by x plus a plus c. So really, either answer, both of those are totally fine. It's just good to be aware that if you're checking your answers against the back of the book or something like that, this might happen. The next case we're going to consider is when the denominator is a product of linear factors, some of which are repeated. Here we're going to find the integral of x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared. So the x minus 2 factor is repeated twice. So what we're going to have is x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared is equal to a over 2x plus 1 plus b over a singular x minus 2, and then plus c over a factor denominator of x minus 2 squared. So had this been x minus 2 to the power of third, we would have had to have a term that was b over x minus 2, c over x minus 2 squared, and d over x minus 2 to the third. In terms of actually figuring that out, with limited time and stuff, it's going to be way too tedious, but what I might ask you to do is to just write the partial fraction decomposition and not actually solve for the constants. That would be how I could test if you understand that or not. But here, solving for the constants is not so bad. I mean, it's a little bad, but not so bad. So we have x squared minus 5x plus 16 is equal to, well, the a is multiplied by x minus 2 squared. The b will be multiplied by 1x minus 2 and 2x plus 1. And the c is just multiplied by 2x plus 1. So now expanding that out, we'll have a times, and what you have to remember is that x minus 2 squared is not x squared plus 4. It is x squared minus 4x plus 4. And then I'll have plus b times x squared, 2x squared, minus 3x minus 2. And then c times 2x plus 1. And I'm going to gather the x squareds together, so we'll have x squared times an a plus a 2b. And then the x's, plus x times a negative 4a minus 3b plus 2c. And lastly, the constants will have plus 4a minus 2b plus c. Alright, now a plus 2b has to equal 1. Negative 4a minus 3b plus 2c has to equal negative 5. And then lastly, 4a minus 2b plus c has to equal 16. And I'm just going to give these equation numbers. I'm going to call this one equation 2 and this one equation 3. Now, because this first equation involves a and b only and not c, our goal is to combine 2 and 3 somehow and get rid of c. And in Algebra 1 or Algebra 2, you should have learned this technique called elimination. So you can take equation 3, multiply it by negative 2, and then add that to equation 2, and the c's will cancel. So if I take equation 3, multiplied the whole thing by negative 2, that gives me negative 8a plus 4b minus 2c equals negative 32. Some books also call this the addition method, because what you do next is we're going to add equation 2 and this new equation together. When you do that, the c's cancel. That gives you negative 12a plus b is equal to negative 37. And I'm just going to call that thing equation 4, just so I have a name to reference it by. Now I'll take the first equation, and I'm going to choose to get rid of the a's. And if I multiply this by 12, when I add it to this equation, stuff will cancel. So that will be 12a plus 24b is equal to 12, or 25b equals minus 25, and you get b equals negative 1. Woo! Now we're in business. Once you've got one of them, it's pretty much game over. And you could have also done substitution. Like if you took this first equation and you said, oh, a is equal to 1 minus 2b, and plug that in for the a, that also works. All right, plug in b equals negative 1 into this first equation. That gives us a minus 2 equals 1. So a is equal to 3. And once you know a and b, go back to one of the equations that has a c. We can use this one. So 4 times 3 will give us 12, plus 2, plus c equals 16. So 12 plus 2 is 14. C will equal 2. Now that we know the values of a, b, and c, we can find our integral. So our integral is equal to the integral of 3 over 2x plus 1, that was the a, minus 1 over x minus 2, plus 2 over x minus 2 squared. So we have 3 times the integral of 1 over 2x plus 1, minus the integral of 1 over x minus 2 dx, plus 2 times the integral 1 over x minus 2 squared dx. So, first one, when we antidifferentiate, we'll get 1/2 ln absolute value of 2x plus 1, multiplying by 3 gives us 3/2 ln absolute value 2x plus 1, minus ln absolute value x minus 2. And don't get all excited and think everything integrates to ln. So this x minus 2 in the last integral is raised to a power of 2 in the denominator. You only have a natural log if you have 1 over an x to the first power. So for this one we use the power rule. So notice that 1 over x minus 2 squared is actually x minus 2 to the negative second. So we'll have 2 x minus 2 to the negative 2 plus 1, which is negative 1, divided by negative 1. So we have 3/2 ln absolute value 2x plus 1 minus ln absolute value x minus 2 minus 2 over x minus 2. Now the next case we have is that the denominator is a product of distinct linear and some irreducible, which means unfactorable, quadratic factors. So first of all, let me show you some examples of unfactorable quadratic factors. So one common example is something like x squared plus 4. Now this does not factor. If you think about it as x squared plus 0x plus 4, the common method to factor this is to look for numbers that multiply to make 4 and add to 0. And no numbers meet that property, so this is actually what's called a prime, or unfactorable, or irreducible polynomial. So evaluate the integral of 2x squared minus x plus 4 over x cubed plus 4x. So that denominator factors into x times x squared plus 4. So we have 2x squared minus x plus 4 over x times x squared plus 4. Now that had to come from a over x plus. Now the thing that's over x squared plus 4 is a linear factor, meaning it's something of the form bx plus c. Now it's possible that you might find that one of those, the b or the c, eventually equals 0, but in general, what you could have had was some kind of linear factor over a quadratic factor. Proving that's actually pretty difficult, but so if you have a quadratic factor in the denominator, a linear factor must go in the top. So now we proceed in the same way. Multiply by x times x squared plus 4, and we get 2x squared minus x plus 4 will equal a times x squared plus 4 plus bx plus c multiplied by x. And that gives us ax squared plus 4a plus bx squared plus cx. So we have x squared times a plus b plus cx plus 4a. Now, not so bad. So because 4a is the only constant term, 4a is going to have to equal 4. Therefore, a is equal to 1. Cx, just c. C is the coefficient of the x. So c will have to equal -1. And then lastly, a plus b must equal 2, and since a is 1, 1 plus b must equal 2, and therefore b has to also be 1. Now that we know the values of a, b, and c, our integral becomes the integral of 1 over x plus x minus 1 over x squared plus 4 dx. Now the first part, easy enough. The integral of 1 over x is just going to be ln, absolute value of x. Now the second part you have to break into two integrals, one of which is x over x squared plus 4, and then minus the integral of 1 over x squared plus 4. Alright, now for this middle integral, we can use a u substitution. If you let u equal x squared plus 4, your du will equal 2x dx. So half du is equal to x dx. So we'll have ln absolute value of x plus 1/2 of the integral 1 over u du. And then the last integral, actually something you have a formula for, that is arctan. So we'll have 1 over 2 arctan x over 2 plus c. And the integral of 1 over u will just be ln absolute value of u, so ln absolute value of x plus 1/2 ln, let's put our u back in. U is x squared plus 4, so in this case the absolute value bars aren't needed. Minus 1/2 arctan x over 2 plus c. And a useful formula that you might need to remember is that the integral of 1 over x squared plus a squared is 1 over a arctan x over a plus c. So, for example, 1 over the integral of x squared plus 9 dx. That would equal 1/3 arctan x over 3. So when you end up with an integral of a constant over x squared plus some number, you're going to have to apply this formula. And that formula should have been something that you learned in your Calculus 1 class. Now, the last case we're going to consider is the denominator contains a repeated irreducible quadratic factor. So something like you have x squared minus 1 squared, like example. So I have the denominator is x times the quantity x squared plus 1 squared. So this is by far the most tedious one we're going to do. So you thought it couldn't get any worse. You're wrong. 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. So that had to equal some a over x plus some bx plus c over x squared plus 1 plus some dx plus e. And you're like, oh my god, I'm running out of letters. Dx plus e over x squared plus 1 squared. Whew! Oh, yeah. Okay, so now when you multiply by the denominator of the left-hand side, you clear that out. The a is multiplied by x squared plus 1 squared. The bx plus c is multiplied by an x and an x squared plus 1. Eek! And the dx plus e is multiplied by an x. Now we expand everything. And we'll have a times x to the 4th plus 2x squared plus 1 plus bx to the 4th plus cx cubed plus bx squared plus cx. And how I got that was I first distributed that x and then multiplied the result by x squared plus 1 using distribution. And lastly we get plus dx squared plus ex. And now grouping terms, so the biggest power we have is the 4th. So you have x to the 4th times a plus b. Next, look for third powers, and the only one is this cx cubed. So plus cx cubed. Next, search for second powers, and we have this one right there, the 2x squared, this one, and then this one. So that will give us x squared times 2a plus b plus d. And then the x terms, we have this one and that one, the cx and the ex. So plus x times c plus e. And then lastly, constant terms, we just have this a, so plus a. And let's work our way from the bottom up. So constant term, a is the only thing. 1 is the constant term on this right-hand side. So 1 has to equal a. So we have 1 minus x plus 2x squared minus x cubed. So 1 has to equal a. Got that. Now next we have that c plus e will have to equal -1. And then 2a plus b plus d. So plus b plus d will have to equal 2. Okay, c will have to equal -1, so we got that. And then a plus b, because there's no x to the fourth, has to equal 0. And now let's use all this information. Since c is equal to -1, I can plug that into this equation, and I'll have -1 plus e is equal to -1, therefore e is equal to 0. Since I know that a is 1, 1 plus b equals 0, therefore b equals -1. And now all I need to know is d, so I go back to this equation. So plugging in all the values, 2 times 1 is going to give us 2, minus 1 plus d equals 2. So that's 1 plus d equals 2. D is equal to 1. Now that we know all the values of our coefficients, our original integral becomes the integral of 1 over x, so plugging in a, plus -1x minus 1 all over x squared plus 1 plus x over x squared plus 1, the quantity squared, dx. Now that's the integral of 1 over x dx. We break this into 2, so minus the integral of x over x squared plus 1 dx minus the integral of 1 over x squared plus 1 and dx, and then plus the integral of x over x squared plus 1 squared dx. Right, now, the integral of 1 over x and 1 over x squared minus 1 are just formulas that you should know. So we have ln absolute value x for the first one, and then minus just arctan x for the second one. Now these other two, we can solve using actually the same substitution. If I let u equal x squared plus 1, du will equal 2x dx. So I'll have 1/2 du is equal to x dx. So I have minus 1/2 the integral of 1 over u du, and then plus 1/2 the integral u to the -2 du. So we have ln absolute value x minus 1/2 ln absolute value u, so put u back in, u is x squared plus 1, and the absolute value bars are not necessary there because x squared plus 1 is positive, minus arctan x, and then plus 1/2 u to the -1 over -1 plus c. So your final answer is ln absolute value x minus 1/2 ln of x squared plus 1 minus arctan x minus 1 over 2 times x squared plus 1 plus c. Now, watch out, because before you try to use partial fractions, you should check and see if a regular u substitution works. So, for example, in this one, you could try to use partial fractions, and you're going to get the correct answer. It's just going to be a little bit different form. But if you notice that if you let u equal x cubed plus 3x minus 4, then du is 3x squared plus 3 dx. And dividing the right-hand side by 3, I'll have that 1/3 du is equal to x squared plus 1 dx. And because this appears in your numerator, this can just become 1/3 of the integral 1 over u du which is 1/3 ln absolute value of u. U is x to the third plus 3x minus 4 plus c. So just be aware of that. That only worked because when I differentiated the denominator, my u substitution, I got a constant multiple of the stuff inside the numerator. And let's try another one. Another thing to be aware of is if you can cancel factors and simplify, you should do so. So this numerator factors into x minus 2 times x plus 1, all divided by x minus 2 times x squared plus 2x plus 2. So those x minus 2 factors can cancel, and we have the integral of x plus 1 over x squared plus 2x plus 2. And let's try to do a u sub. If I let u equal x squared plus 2x plus 2, du is equal to 2x plus 2 dx, and I have x plus 1, so if I take and divide that by 2, I have that 1/2 du is equal to x plus 1 dx. So this will become 1/2 of the integral of 1 over u du, or 1/2 ln absolute value x squared plus 2x plus 2 plus c. Now here, use substitution and partial fractions to find the integral of cosine x over sine x times the quantity sine x minus 1. So you can combine the partial fractions technique and substitution to evaluate integrals of this form. So if you let u equal sine x, then du is going to equal cosine x dx. And then my integral becomes the integral 1 over u times u minus 1 du. And we can use partial fractions to evaluate that. So 1 over u times u minus 1 will equal a over u plus b over u minus 1. So 1 will equal a times u minus 1 plus b times u, or 1 equals u times a plus b minus a. And so then negative a will have to equal 1, so a is equal to negative 1. And then a plus b, because there's no u on the left-hand side there, a plus b must equal 0. So since a is negative 1 plus b equals 0, and therefore b is equal to 1. So my integral, this becomes the integral of negative 1 over u plus 1 over u minus 1. So we have negative ln absolute value of u plus ln absolute value u minus 1 plus c, or plugging back in our substitution, negative ln absolute value of sine x plus ln absolute value sine x minus 1 plus c. And if I flip those around, I have ln of sine x minus 1 minus ln absolute value sine x plus c. So this is totally fine, like that's a completely correct answer, but just in case you are doing your homework and something simplifies funky and you're checking your work, you can combine these logs into the single log ln sine x minus 1 over sine x plus c.